Michelle. So let's begin. So today's review lecturer is Sven Krippendorf from the LMU in Munich. And Sven will be talking about how we can learn mathematical structures. So thanks a lot.
Yeah, thank you very much. Thank you very much for the invitation. It's great to be back in Cambridge. And yeah, let's keep this interactive. So please ask questions at any time. I think we have 90 minutes. So let's, ask. I'm happy to explain things in detail, especially because we are from a mixed audience, everyone gets the most out of this. Especially we're also, a small crowd, so please not feel shy to ask questions. So let's start very simply. So as physicists, we often come across and use formalisms, algorithms to describe dynamical systems. And so as students, we are taught to learn them. And as physicists, we try to develop or apply them. And so one example could be, say, something like Hamiltonian formalism, Hamiltonian dynamics, where we have a very good prescription of how to describe dynamical systems with this. But we usually are taught not to ask why questions. So we are usually, told this is not a good idea to do. But we can also formulate it in not a why question and ask, what makes these formalisms special? What is significant about those? And it turns out that there is a simple answer to this, namely that they are very efficient in describing these systems. And this is a key aspect of this whole story, because this will turn out, this makes such formalism susceptible for optimization. And so this is going to be the topic of this talk. How can we leverage this efficiency to find mathematical structures by formulating appropriate optimization problems? And this is obviously something which is very deep, because this will influence physics as we do it now very profoundly, I think, over the next decades. And so we should really, think about where this can go. And so this is nothing else about things like, if we're thinking about scattering of particles, how should we describe it? They obviously are taught, first of all, to use Feynman diagrams to do this, often very much. Then if we are going to, different parts of the theory landscape, we would be taught to use something like the amplitude-hedron or so. So these are things, obviously different formalisms that are around which describe that, but we don't know what is the best one. And clearly that is always open for debate. And this can be put also into the question of, how should, or could ask differently, how should we utilize the situations where we have many descriptions of dynamical systems? So this is the question about dualities. So when we're thinking about various dynamical systems, we have various dualities to describe it. Maybe there's something good behind all of this. And clearly, one aspect of this whole story is also, are there some new mathematical structures underlying our favorite dynamical systems, such as field theories, etc.? So you have a whole program about looking for symmetries or generalized symmetries, etc., for these things. And this all territories which we will tap in with machine learning. And so this is obviously in the long term what we have in mind, and where I think we bring a new angle to this whole story. And this talk should kind of introduce how we can, and review how we can do this. And I'm obviously happy to talk offline. We are live on YouTube. So about some short-term or mid-term goals this week to see how we can make progress. But I think it's rather remarkable that with machine learning and with this optimization view, we can have a new angle at these kind of questions. So let's start with the basics now. With what do we mean with actually talking about efficient description? And so let's start with a very simple dynamical system. So a very simple dynamical system might, look at a classical dynamic system with multiple particles having various masses, and they interact via some potential, right? So this is something that you can look at, and well, we can try to predict the dynamics of such a system, right? This is nothing very fancy, but this obviously, once we always predict such dynamics, we can also measure how well is such an approximation doing. How good is it, in predicting those dynamics? So if you had a model that's shown here on the right, you would ask, okay, well, you could measure the deviation from this and see how well we are doing. So let's go through how we would go about this. And again, it's a very simple setup because such dynamical systems we can simulate. Right? We can simulate them solving your equation of motion with your appropriate numerical solver, for instance. And then you get trajectories. So that's the data that you have. And now you want to have a model that predicts the, say, next time step, for instance, of this story. So you are targeting this, say, for instance, if we're talking in the context of Hamiltonian dynamics, you talk, for instance, about predicting P dot and Q dot given as input P and Q. And you will have a model that is kind of mimicking, trying to make this prediction. And this can depend on some parameters, theta. And then you can, fit this model, you can optimize this model, and you can evaluate this model by comparing with the deviation from simulated data. So if you have somewhat your simulated data, you have your predicted data from your model, you can measure the deviation across various phase space points. And this gives you some energy functional, some loss function, however, in whichever language you want to calculate this. Right? So this is something which you can optimize. Good. Now you might wonder, isn't this just bread and butter fitting and designing models, which we have been doing for centuries as physicists? And the answer to this is no, because we have much more control now. In particular, as I will argue, that by using automatic differentiation, we can search for different mathematical structures and demonstrate their efficiency. So I will come back to what automatic differentiation is, but just as to create a bit of sense of the audience, who has heard about this term of automatic differentiation before? Okay, a few of you. So let's I'll come back to this in a second. So good. So as I was showing on the previous slide, one idea is that, okay, so you have your inputs and you want to predict what is the next time step, essentially, right? So this is the model. Now to show you where, so yeah, let's talk about this kind of baseline structure then for 1 second. So now in this context, this could be anything, this kind of model. So let me second. So the baseline structure they don't work? Okay, good. But you can see anyways, I think. But I was wondering about the video. So The baseline model is something like this, right? So it takes in PQ and it gets theta and has parameters theta. And what you're getting out of this is, say, P dot predicted, Q dot predicted. And the loss that I was writing down beforehand was something like this. P dot, let's write it in terms of M. So this is the zeroth component of your predictor M I theta minus P dot P dot. And you just take the absolute value squared. Now, what do I mean with how this procedure is working? So now think of this M, for instance, as a neural network, which I will be thinking of as very much. So M as a neural network. So even, you could think of something like as a cartoon picture like this. So you have your inputs P and Q. You apply some linear transformation to those. Weight it with some bias. You apply some nonlinearity. And then you do the same thing again. So this goes you to this intermediate layer. You apply this again. AI is something else. And so this could be your model F. So you're taking in P and Q, and what you're getting out is something which is not necessarily directly what is P dot Q dot. Right? Now, how do you can obviously plug this in, and you can measure this. And now, what is the idea? The idea is that, for instance, via using some version of gradient descent, you can optimize your parameters. Right? So, for instance, you could calculate at time t, plus some delta t. You will take them as your parameters at time t minus the derivative of your loss function L at time t. And so this is the standard picture of that. If this is your parameter, this is your loss function, this might be something like this, and you are just moving, this is at time t, you're moving down ideally to a minimum. So now, and automated differentiation comes in when we want to evaluate this guy. So what does this do? Is this basically, this is something I can clearly program. This is just a linear map with some non-linearities effectively. But what you can also have available is because these are basically just some linear function and some known non-linearities. Think about the sigmoid function, think about a polynomial or so. We know what the derivatives are of these. We have a really good clue about what are the derivatives of this function. And basically, what you can do is instead you not just have m available, but using the computational graph of this function, you also have all the derivatives with respect to all of the parameters available. And this continues actually. You could even, go to higher derivatives, etc. of this whole story. Now, I'm stressing here that this is coming that that we will have to use these derivatives, right? So we will use them here, and we have to use them obviously with high accuracy, right? I mean, it is not something where if you want to get to very good results, you don't want to be stressed with finite difference methods. This is something really because we do know what the derivative of this whole story is of this function. We can evaluate this at machine precision. And I guess if I ask now who's familiar with Mathematica and using Mathematica, I will see all hands effectively. So Mathematica is doing this under the hood effectively as well. And the only thing that this is doing is that it's also simplifying this expression. But basically, we're not doing anything else, right? We are using very well-known building blocks in this neural network language. And we want to take derivatives of that. And this is something which is being done always in this in neural networks. This is very much bread and butter, and by now this is also very efficient. Yeah. So when you're doing this in terms of neural networks, you are doing this with respect to 1 millions of parameters, right? This whole story, and you're evaluating these things very often. Right. So we can do this very well. Good. Questions on automatic differentiation? Good. So now, because this is a very important tool throughout all of these works, because when we talk about physics frameworks, of mathematical frameworks, we often can formulate an optimization problem in terms of derivatives of that target function. So think about, for instance, Hamiltonian dynamics. So if you had a network which was predicting the Hamiltonian, yeah, instead of the model, you can use this automated differentiation, so this knowledge of this derivative, to calculate P dot directly. Yeah, so let's make this very explicit in a second. I think in the next slide, let me check. Let's have a look here. So now let's do this here now as well. So one thing, when I do something like this, also to be very, very explicit. Now, yes, yeah.
Yeah, so for the automatic differentiation, do you also have derivatives on the inputs available?
Yes, we do. That's exactly what I want to write down here now. So just to be very precise on this story, because so good. So now we have this loss function here, which we were writing down in terms of m outputs, yeah, as p dot. Now, how does this story change? So let's write this. Let's write this out. So you would have here, if you're predicting P dot, you will have del H, del Q, which was one of your inputs. Okay, let's get the sign right. So this is plus P dot. That's one aspect. And you would be interested in having del H, del P minus P. So your loss function would be modified to something like this. And I'm happy to, chat about this, but and the how to go about the explicit implementation of these. But basically, this is pretty much very much straightforward, to implement. This can go onto something like this, jack spread of your function h with respect to, essentially that's what you will have to do. So this is essentially it can show you code examples where this is just a one-liner, and then your loss function just involves this term. And because we do know this expression analytically with any ansatz, we can use it in something like this. And this is obviously, I'm saying this for multiple reasons, because I wouldn't be standing here if this wouldn't work. And talking about this. So for instance, okay, let me get this thing away. Because now you can, for instance, you can do this story, you can set it up, and you can compare what happens here for what happens in the story with just a simple gravitational two-body system. You can simulate. You can try to make this prediction with just a standard feed-forward neural network. So just a couple of dense layers, essentially just a few more of these effectively in here, and try to predict it. And you see that you will not be very accurate in doing this sort of story. But so the comparison, doing the same kind of model architecture, you're predicting the Hamiltonian, using such a loss function, you are getting better predictions out. So this is interesting, I think, because this really, comparing more or less apples with apples kind of models in terms of the complexity that you're putting in, you're getting better predictions out. And now this is obviously something which we can understand by now, because we put effectively what we often call a bias on this whole optimization story. Namely, we are enforcing by this kind of constraint, for instance, that the energy is conserved of this in this system, and that puts you onto trajectories which are very much more favorable to this problem. Now let's sit back and think about this for 1 second. So what have we actually done here? Because when we do this kind of simple thing of writing down such a loss function here, in my training data, I did I have the Hamiltonian in or not? Did I use it? Yes or no? No. Good. So I did not use it, right? So this is important. This is an important insight, because I really did not have to know about the actual form of this Hamiltonian. So I can if I have a way of observing this system, if I have a way of simulating this system just by looking at some equations of motion, I can look at things like I can infer the Hamiltonian. So now this is important, I think, because when we are thinking about looking for mathematical structures, we're actually in a situation where we do not know what the structures are. We do not know, for instance, what the symmetries are of the system necessarily. We obviously can think about it very carefully, but a priori, we can be in situations where we do not know the symmetries. So now, this is the question, okay, can we put up, okay, so talking about symmetries, let's think about, can we, can we do this as well? Can we learn symmetries of this story? And the answer to this story is yes, we can do this. And we have to go through the machinery again. Yeah. And so this involves looking at, classical mechanics and thinking about how to formulate this as an optimization problem. So we do know that any symmetry of the systems is associated with a conserved quantity. And we do know what the property of a conserved quantity is in Hamiltonian dynamics. Namely, we do know that the Poisson bracket of this quantity with respect to the Hamiltonian is actually vanishing. So now we can actually search for something like this. We can formulate this, and we can formulate this as follows. So we have to put up on our engineering head, and we have to set up a new neural network structure. This neural network structure is modified as follows. Basically, we have one network which transforms our input to some, generalized coordinates or candidates of generalized coordinates, called here P and capital Q. And then we continue with our Hamiltonian network. So this is what we can set up, and we have to obviously go through the algebra of seeing what the conditions are on these variables, and they are given by essentially looking at this. Sure. This is not that hard for this story. So what you effectively have to do is, okay, you will have. That's why I skipped put to the next slide, because you just basically write down on pen and paper what are the conditions, and that's what we did. Obviously, it depends a bit on how efficiently you formulate all of these constraints effectively, all of these conditions, but it's all pretty much doable, yeah, with reasonable effort. It takes some time, right? And I'll comment on this in a second. But basically, once you have these equations, you code up these losses, and you are starting to trying to optimize. Now, and clearly there are a couple more constraints, like you have certain constraints on the other on the Poisson brackets, which you also have to imply. But then, yeah, you can do that story, and you can be successful, right? In this story, and this is nice because you can get this to, so yeah, with this effort back then, we did this on several classical dynamic systems, etc. And we can not only see this performance, yeah, so it does it does work nicely, but we can also go further and ask about what insights we get then. This one? Yeah. Good. So this, good. It's left as an exercise. No, but it's a good exercise in some sense. So effectively, right? Now, what is this constraint here effectively, right? You are looking at appropriate derivatives, right? That you have to write down. So you will write down effectively, yeah, what is, you write out the Poisson bracket in terms of derivatives, and each of these derivatives is accessible via automatic differentiation. And then, you know, you basically end up with loss terms, which characteristically look something like this one effectively, yeah. But, yeah.
So if this classical mechanics, is there any instruction for me thinking about classical gravity and applying it to that? Because there is much in, and if I give you a metric to find conserved quantities so that you know that it's like integrable stuff, you could find like higher, like killing nano.
Yes, yeah. So it's not limited to that, but the applications have not been done. But the framework is there and just to be applied. And yes, we should talk offline about these things. But that's exactly, I think the framework is there to do all of these kind of things. And I'll give you a bit of an overview of, you know, how far we've pushed it so far. And, you know, how other of our work relates to these kind of more sophisticated systems, because you might have to go up a notch a little bit in order to make this actually, solvable. But in principle, there's no obstruction. Yeah. That's why I'm very excited about this whole stuff, right? Because this is actually very, you know, it's very, very much interesting.
But to apply it to a real world system. You're going to have, then you said that's so far, there's one set.
Yep.
You managed to find all the x. So not many because too much,
yep.
But maybe for finite.
Yep. Yeah, good. So here, so simple system, effectively, I think this is a two-body this is a two-body system, I think. So you can ask, okay, what are the conserved quantities in this system? And so I'm showing you here this. I mean, you can get more sophisticated than two-body and three-body, things like this, right? So you have to go to things like graph neural networks, etc., to make use of a couple of symmetries to make this go scale to larger systems. It's going to be done, but nevertheless, I think this is already instructive. So here, for instance, you know, you can see that angular momentum is conserved, right? So you basically you open up the box. You see what you're getting out in these here in this intermediate layer, essentially, to ask exactly, what are we computing here, right? And that is shown you here with a very simple, you know, here we know, okay, it's kind of a polynomial that we are looking for, but clearly there are much more sophisticated methods on the market to address this, you know, doing symbolic regression, etc. to do this. But nevertheless, I think it was quite remarkable back then to actually do this, to see that this is coming out. And you can play games about, like, for instance, normally we don't know how many symmetries we have exactly, right? I was anticipating that question. So you can play this game. Okay, what's happening actually because you have this kind of as a hyperparameter effectively, of, you know, to run the machine a couple of times with one conserved quantity, 2, 3, and 4, etc. Right? And you can do that game and see, you know, how many you see and what the results are effective, right? And you see, okay, actually, like on the quantitative side of things, what is happening, you know, what is a good number. Yes.
So how do you know that there are not multiple extrema, so that we are one extrema, you get some of the quantity, but you don't see the other, and the quantity can find that.
Yes. So good. So there are two comments I want to make on this. So one comment is this absolutely can happen. Yeah. I don't think here this happens very often in this story, but this is something really to keep out, and I think will be very exciting, because especially if we go to much more sophisticated setups, yeah, where, you know, this is not just that, where we actually, you know, might want to see these two descriptions or so popping up. We might see this. Yeah? So that's something that would be also, again, very exciting to discuss this. The other thing why I like to put this out here is that you sometimes have to be careful in how to interpret these latent variables, right? Although you run it multiple times, you secretly might it looks at the first sight maybe different results, but it's just in some sense a linear combination that it's finding out of the other one. So that's what one has to disentangle. But I mean, we're physicists, so we can do this, right? So now let's put up a notch. And so now this is something like where symmetries was for finite number of symmetries. Now, how about when we have infinite number of symmetries? Yeah, can we do this? And again, so this was again 2021. Now we can do this. So again, so who's familiar with Lux pair Lux connection in this audience? That's another who has heard this before. Okay, good. Similar as automated differentiation, right? So that's but different people. So good. So let's go. So let's go up a notch a bit. So basically, there are systems which have a lot of symmetries, and so you can have additional constraints. So for instance, so here we saw previously that we had this constraint, this single constraint, and now we can go to situations where we have as many as their degrees of freedom, effectively. So in the sense, if we have a system which is 2n-dimensional, is integral if and only if they're n-independent, everywhere differentiable integrals of motion, right? So now this, on the technical side of things, one has to be a little bit careful, right? Because you have to worry about that you get still find the optimal solution. So if you're going to such systems, do you actually find this? But there are alternatives around, and there are alternatives around from physics and mathematics that tell us what other conditions we could be checking for in order to show that this system is actually integrable. And this goes into the realm of looking at Lux pairs and Lux connections. And so, for instance, this is a matrix where let's look at the Lux pair, for instance. So we have a matrix valued equation. L dot equals to the commutator of LMM, such that the equations of motion are satisfied. If you find such a solution, then the conserved quantities are given by the trace of L raised to the power k. And now let's look at a simple example, namely let's pick a harmonic oscillator. You can, which we hopefully, now if I ask, okay, who has seen the harmonic oscillator, hopefully would see all hands raised. So we do know what the equations of motion are. In this context, you can write down a Lux pair, which would look like this. And if you raise L to the power, you would see this. Sorry. Now, why do I write this down? This whole system, because this is something again which very much looks like a system that I can optimize for. Now, however, very good. So a priori, I don't know. So this is also on the next slide. Effectively, this is not unique, the Lux pair, right? So in some sense, there are parameters here which I can freely choose, and this is effectively something which when one tries to put it on the machine, always one has to keep an eye on to see what the machine is actually spitting out, because it can the result that you're getting out is not unique necessarily, right? It's unique up to certain transformations effect that you're encoding. Good. So bit of motive. Probably, yes. Okay. You can see it exactly like that, and then exactly. So that's exactly. I mean, you can play all of these games, I think, correctly. Yeah, but I put this here. I think. I mean, this is also like upper. So in this case, obviously, we do know everything, right? But put yourself in a situation where you don't know everything, right? You want to ideally have a system, a machine learned system, yeah, that can deal with these things. So you have a way of tackling this, right? Because we want to be able to make sense of these results. Good. So now this is now when sitting through talks about integrability, oftentimes, you come across these equations, but when you ask the speaker about, how did they get there, it was often, known for for decades, or it's kind of a good lucky guess. And this is kind of summarized in, I guess, in Nicholas Beidel's lectures. So where he says basically having a Lux-pair formulation of integrability is very convenient, but inspiration is needed to find it. It's a structure, it's hardly transparent, it's not at all unique, and the size of these matrices is not immediately related to the dimensionality of the system, and the concept of Lux pairs does not provide means to decide whether any given system is integrable unless you are lucky to find one, right? And to find a sufficiently large Lux pair. So this really when smells to, we can search for these by optimization and let the machines try to find those. And clearly there are applications that one can think about. And I'm not an expert on integrability, but maybe some of you are. And I would be very excited to hear, what are, big things that one could, that people have failed so far in finding ones. So let me give you a little bit of a flavor of this story. Again, we want to find an optimization problem to find these Lux pairs, again without knowing the Lux pair, right? I mean that's the game, and we continue our story from before for searching for symmetries. Now the functions that we want to approximate are these matrix values L and M, and we have this condition, so we formulate this as something we want to solve. Now, there are certain problems with this because this is not enough. Yeah, so you have to be very careful in setting this story up, because you need to ensure, for instance, that the pair there's some equivalence to the equations of motion. But this is where your engineering head gets on, and how you can ensure this whole story. So, for instance, this tells you something about how you have to engineer L, and what condition Lm has to contain. For instance, here this has to contain the right-hand side of the equations of motion, and the L has to contain the left-hand side of the equations of motion. And you can formulate this, that some component has to include this. And you can formulate this again as a loss function, effectively. And this is what what is written down here. And again, this is something you can code up. Yeah, I mean, it takes some time, but this is doable. And good. So now this is still not enough, because these networks are trying to find simple solutions. And if you're thinking about, for instance, just the first couple of two, think about L and M being just 0. Yeah, you would solve it. Yeah? And so that is not something which you want to allow for your neural network to do. And so in this sense, you are looking for avoiding mode collapse, essentially, for these components of these matrices. And so this then thanks. So then you end up with four components to the loss, and that is your optimization problem that you want to solve. What I'm minimizing here is that I want to ensure that one component is equal to of this matrix is equal to the left-hand side of the equation, right? So it has to appear somewhere in this matrix. I don't know where. and I ensure this in such a way that this is can happen anywhere. Yeah. So this is not restricted to this location or that location. I'm not fixing. Yeah.
No, and then second and the third also can be not can be.
This one.
Yeah, yeah.
This is the right hand side, right? So the right hand side of the equation of motion is like, if your equation of motion looks like x dot equal to f, effectively, then that f is written here.
So could you have written the CIJK L dot minus P dot? That's what
Some component. So here, so this
just like
no. So this is all components, right? So this is x and p.
oh, it's
Yeah, it's space-based. It's space-based. Yeah. Otherwise, I would end up with even more messy slide. I don't, this is already very messy, effectively. Yeah. But again, this is something, which you can set up and calculate. Now, for setting up for a simple system, again, this is also the thing that we have to train this on, right? It's just samples and phase space. Yeah. No knowledge about Lux pair whatsoever. Yeah. This is just you simulate the system. You have points and phase space. That's all you have for training this. Now, obviously, L and M are going to be some sort of model, some neural network, and but again, so you choose. This is again a lesson in some sense, because you choose it always as complex as you need it. And so if we're thinking about a harmonic oscillator or so, we don't need a really fancy neural network, right? We need only a few parameters to model this whole story. So in that sense, you look at the complexity of these networks that you're kind of expecting, and then you choose them accordingly. Good. Again, one thing that did help us a lot in doing this study was to, for instance, when we see results, is that we often are not converging to things, right? That's a standard story, and you can understand when do you not converge, for instance, right? You can initialize close to a solution that exists, and then you go slightly away from it, and you see at some point, okay, it stops converging. And what you see is that, for instance, the problem is off-diagonal terms which should be 0 are not effectively set to 0. And so this is something. These are things that you can work against. Yeah. So you can by engineering choices. So for instance, you can deactivate certain nodes by appropriately modifying your answers. Good. Now here are some let's start with a simple example. So you do this story for harmonic oscillator again, and you end up with a Lux pair, and you can check what you're getting out, and you can see that you're getting out essentially the Hamiltonian as expected for this choice of parameters. I forgot what omega was in this setting, but this was exactly what you will find. So that's nice. Then okay, you can go about doing the same story once you've set it up to solve this for other systems. So we did this for a couple of systems, also things where we have to go to a Lux connection, and so to show a bit more sophistication effectively. And we could get this to work for these systems as well.
So fix it on a value of A. So you said that, as you said, L was kind of, I think it was up to a 1/20 factor.
Yeah.
So when you finally, when it works with the system, does it pick a value of A?
Yes. Yeah. So it picks a value of little a. Yeah, that's what you're saying, right? Yeah. Yes. I mean, that's what you're converging to. So, but this is why, like, if you do it run from some other initial condition, right, you end up with a different combination. It doesn't fix you always to the to the same one.
So that's saying that the determinant of the L is the Hamiltonian, right? So is the Hamiltonian optimistic factor is mine, right?
Yes, for instance here, yeah. So for instance here, I think yes, the answer to this is yes. So for instance here, right, what do we see here is in this context is 0.2 times the Hamiltonian effect. That's exactly that, yeah.
But sorry, so this L and this N, you give there certain choices around the.
Yeah.
This has the structure of the L and N, you know, right?
Yeah. Yes, so in that sense, you can check it, right? So you get something out, right, for L and M. And you do see, okay, yeah, what does this equation, is for instance, is this equation satisfied, right? So I'm evaluating here, for instance, the left, so this result here, L dot, right? So you see this, and this is what you're getting when you're evaluating the commutator, right? So I'm showing you this here because you can see how close you are, how good you are in evaluating this story.
But the L and the M you got them are sort of ones shown on the previous slide with certain values already.
Yeah.
But it's not on the nose. It's a certain value.
Yeah. But I think the nice thing about this whole story is, right, so once we've given some L and M effectively out of it, we can check, yeah, how well this is doing. So for me, this is very transparent, like when I want to search for something, you know, in some differences, because again, I can look, I can plug it in. Good. Now, this is another story then that we did.
I have one question. So
Yeah.
how big are those in the harmonic oscillator?
I don't remember the exact losses of this out of the top of my head, but I can show you a couple of losses here, for instance, right? And then in that sense, and this also depends on the setup that you do, right? I mean, you know, and how far you push it. But so here, for instance, we push it up to kind of close to machine precision, effectively.
Okay, in another sense, how does it deviate? How big are the deviations from the known Lux pair that you're already?
Ah, good. So I mean, this Lux pair is only known up to whatever. This is only known up to, you know, certain transformations, effectively, right? So you always see it very close to some transformation. So that's what you. But I mean, we were able to see the structures that we had. Good. Now another story is, and you know, this is like talking a little bit with integrability people, and also, you know, knowing what's been done in talks, is effectively if you've given some system that is known to be integrable, you might want to try deform it. So you want to add perturbations to your Hamiltonian, and you want to ask the question: does this system remain integrable or not? So and here you can again play the game, and the numerics are also favorable for this, because you can do you can make a search. And how does this work? So in this case, you start with a known Lux pair. So you initialize your network at a known solution for the unperturbed system, and you see how it reacts. Yeah, when you add that, when you confront it with data from that perturbed system. And here's how it does. And so for the integrable perturbation in this case, it really, you know, knows how to adjust and goes into that direction. But for the non-integrable perturbation, it doesn't come down, right? And so these are also things like, okay, that gives you some indication of, you know, when do you want to call something integrable, or when you see something being converged, because this can be used as a measure of, you know, how well this is doing. Again, yeah. And basically then let it try to relax, right? Let it try to relax to the new solution. And again, this is, I think, nice because you can this is basically an automated pipeline effectively, right? So you can search for all sorts of deformations effectively. And so you could think about programs of doing this for other systems where you want to systematically search for such perturbations. And now there's obviously one interesting story to this bit is because, like, okay, this doesn't mean that it's non-integrable necessarily. I mean, here in this case we do know it. It could be that the Lux pair that we are using is just too small, right? So at this moment we can't account for that, right? So we're just searching for that, but it's a we can be lucky. Yeah, that's the ansatz we gave it is too small because it could be just yeah. Maybe there's something smart to be said about this kind of story as well. How to embed it into a larger Lux pair. Okay. Good. So, but nevertheless, I think we can do this for with machine learning now, right? I mean, this whole story is, I think, is nice. Again, what is open, I think, is what would be the most pressing question in integrability this should be applied on. So I'm happy to discuss. And again, the key insight for this whole story is to formulate this search for Lux pair as an optimization problem. Yeah, to write down a loss function which you can optimize for, so you can generate data just simply from space, and solve this optimization problem. Good. Questions on this part? Because otherwise I can entertain you a little bit with the following. Now this is very much well in known territory, right? So we are in situations where we do know, okay, we know this system looks integrable, yeah, we want to search for it, and so on. We might also want to think about questions where we don't know which structure we want to search for. Yeah, and I want to highlight that we should not disregard neural networks in this respect here as well, but we can also use them, yeah, to identify structures.
So by the algorithm, you still need inspiration to make an ansatz.
Yep.
That's inspiration. But there is no sense in which you say, oh, I give you a system, I give you the paper of the system, and then this person will get an ansatz to generally go to it for LM.
Yeah, good. So very good. So I think this is then becomes a question of converging and setting up your machine learning appropriately and so on, because this is pretty much very flexible, right? LNM, right? I mean, the ansatz, that's I think where the power lies of this story, because the amount of ansatz that you can go through by putting it on the machine is just enormous. Yeah? The machine does not care about whatever 1,000 by 1,000 matrices and stuff like this. Yeah, yeah. But the ansatz can be very, very flexible, right? And that is really the story to us. Okay, good. So can we find structures without clear optimization? So again, okay, yeah, this is what do we do when formulating the optimization problem is not possible. And the insight here is that your neural network trained on some simple inference task might already do some sensible ordering of your data. And is there a way of connecting this with an understandable frame? So making sense of whatever the neural network is doing. And so this was, again, relatively early. So this was 2020. We looked at this. We wanted to ask whether we can, again, search for symmetries in this story. And so can we find again what are the symmetries of such a potential, for instance, simply without formulating this kind of optimization problem. And what we need to do is basically the following thing, that we need to group in this story all these kind of points, they should be grouped together. And these points should be grouped together, right? Because they correspond to the same symmetry orbit. And they are, you know, although they have the same value of the potential, yeah, that's it. That's the information that we easily have available. They are structurally different. And so the story is that basically the thing we want to explore is that we put in as an input x and y, and we want to classify which of these classes the potential lies to, right? So this, for instance, these 2 points would lie in the same class. Yeah? These 2 points would lie in the same class, etc. That is the task we ask it. Now, why is this? So this inspiration comes from obviously that this kind of story of embedding things in a meaningful way is something which is being observed in other domains. So, for instance, if you're looking at, again, an old story in languages, you see that in such late layers or embedding layers, things with the same meaning are grouped together. So, for instance, if you were to calculate the Euclidean distance of the vector England minus London and the vector of Paris minus France, then they would be similar, and actually the locations of these would also be similar. And so this is something which was, you know, also brought to the sciences. So this was used to rediscover the periodic table and to look at the scent of molecules. And we wanted to ask, can we search for symmetry symbols? And the answer to this is yes. So in this example here, for instance, I'm showing you here a visualization of this latent dimension. So this is this embedding layer. This is in general something like, you know, think of this as some 100-dimensional vectors essentially that you have. You want to project them down. And you want to project them down efficiently. And so here, this is what shown with some stochastic neighbor embedding. And there's some hyperparameter tuning going on. See? But then you start to see structures, and these structures are in such a way that they separate these islands from each other. Now, this is part of the story, because once you have something like such an island, you want to know what structure is behind it. And again, you can design an algorithm to search for, say, the generator that connects all of these points. This is essentially by looking at, okay, what is happening with, you know, how are we connecting these dots with each other? It's basically, okay, we have some infinitism, we have some generator, and this is how our nearest neighbors are being connected. You can do this obviously a lot of times, and see what are the dominant components here. And when you do something like this, you will see very much singled out what are the generators of this story, and you see that the others are not contributing. We can push this to other examples. So here are examples for SO4, SU2, and SO3. And you see obviously that the performance of this whole story is you see always this kind of jump effectively. You see you see dominant components. You see roughly how many points you're needing, right? So this whole story depends on, you know, how many points you have and, you know, how noisy these are effectively. But it's relatively insensitive. So if you have something like, you know, here is 100 points or so, here it's 500 points, and the data is in that sense is cheap in this case, you can still work with it. But and there are lots of games that you have to see in terms of you go to higher dimensions that you can deal with. So these are somewhat more non-trivial. Good. Now you can play also other games. So basically do things about putting these into higher dimensions. So imagine the situation where you have MNIST images and you're asking, okay, can we apply this whole story still to our 784 dimensional images, which basically, so these are 28 by 28. And then you see that here in this case, right, this 8 is rotated, for instance, and you can ask, okay, what is the symmetry on these kind of objects? And again, in this story, you see one dominant generator effectively being built out, and that is nicely corresponding to that rotation that we are looking. Good. Now, in the last kind of 20-ish minutes, something like that, let me show you a little bit of different flavor of things, because this whole story is obviously very nice, but your domain application might require some more sophisticated tools. And by now we have tools for other problems where this becomes very where we can solve not just a 2-body or 3-body problem, but problems of actual interest. And so the story I think I'm going to tell now is about Calabi-Yau metrics. So this is done in collaboration with these people. So these are 2 papers which are out by now. There are more to come. So one is going back to 2012, and one is which was recent with Matis, and then there's also ongoing work with Piotr and David. And most importantly, that's one thing I'm very proud of is we have some software effectively released that also shows you a lot of automatic differentiation on that. So please feel free to look at it, and there are lots of nice tutorials about this. Again, this is a story which is on the numerical side of things is quite old, and so I think so there is a lot of work. Damian is here in the audience, for instance, right? Who has done some work in this, but this goes back to 2005. Then there's a work from Donaldson in 2005, and then Douglas and collaborators were starting this. There's work from Frederick and Nasser in 2009. And then there is the whole machine learning story of this. So what's the motivation? Motivation is rather simple. We love extra dimensions as string theorists, and so the question is about the metric of these spaces. And we obviously, by writing down something like the Einstein-Hilbert action, we do see immediately that the metric is important. So this is nothing that should argue. I mean, we can argue about, okay, what is the most pressing phenomenological application, but they are definitely around. So I mean, the one thing that I'm interested in is to really understand the effective field theory that comes better, that comes out of string theory better. So to understand things like, okay, yeah, what are these kind of prefactors, for instance, and so to understand, okay, are there some constraints on these spaces that we secretly did not see before? Good. But this obviously is not just limited to physics. You could ask about, from a mathematical standpoint, can we identify numerical or analytical solutions to Calabi-Yau metrics? And this is something which people have not been able to do, as I will say in a second, so far. And neural networks in general are very flexible function approximators. You can ask in general, okay, can they be also useful approximators for these type of mathematical structures, namely these metrics? And also in particular, they can be useful to solve PDEs. So are they also useful to solve Einstein's equation? So let me say a little bit about the object that we're interested in. So the object that we're interested in are Calabi-Yau manifolds, and this comes basically out of the standard old story that we're interested in supersymmetric solutions of string theory, and we know that they exist if we construct Calabi-Yau manifolds. And the example I will study today is the hypersurface in P4, the quintic hypersurface in P4. So this is basically, taking this kind of hypersurface, and psi is your parameter. Yeah, so this is a one complex structure modulus parameter that you can take, and we are interested in the metrics that are varying across psi. Yeah, so how is the psi dependence of these metrics? And obviously, we do know that such a metric exists, but they are not explicitly constructed, right? So Yau in 1977 showed that these metrics do exist, but we could not so far construct them explicitly. So good. Now you can let's see essentially. So what the condition that you can put on this Calabi-Yau is the following. The condition that we essentially will be interested in is the following. So these are listed here. So you will have a complex 3-0 form omega, and you'll have your Kähler 1-1 form J, and they have to satisfy certain conditions shown here. And you see, for instance, in particular, also this kind of balancing condition that you have to satisfy. And as the whole theme of this talk is about optimization, you can see where this is going effectively, right? Because this is essentially, again, some optimization condition, yeah, that you can formulate this story as. So can we solve this? Yeah. And now we have to be explicit. Again, we have to make an ansatz for these metrics. So we have to look at particular examples. So here for the quintic hypersurface, we know how this 3-0 form looks like, and then we can look at the metric. And so one thing is that essentially we can look at generalized Fubini study metrics, and they can approximate the metric of your choice. So this is essentially the crucial line. So you have a Kähler potential, and the log of K is given as such here. So it's basically these sections here, which are, think of these as polynomials in Z, right? So, and this depends on the degree that you want to choose this at. The higher the degree you choose, the more accurate your approximation is. Think of this in terms of if you're Fourier modes or so, yeah, you have more modes that you're taking with. And what is the object that is allowed to vary is this H matrix, right? That's the whole story. Now you see immediately how automatic differentiation comes back to the story, because what we're interested in is the metric, for instance, of this story, right? The metric of this story is given as a second derivative of the Kähler potential. Now, and this is shown to you here. Right. So given a framework, where we can formulate this, and where we want to, solve certain properties of the metric, we want all to be able to evaluate this. And this is where, automated differentiation becomes in very, very handy. Good. So that's the object we are interested in. Now you can ask, okay, yeah, how well do people have done people before, and how difficult is this problem numerically? And so the thing that made some advances in this are essentially these spectral methods, which we are with our ansatz also following by Donaldson et al. But their algorithm is not very efficient. So in some sense, this is some way of how this is going in terms of, you think about accuracy on the resolution here on the x-axis, and that's the time of a subset of the things that need to be evolved in to run this algorithm. And you see, okay, this is blowing up very much. And you have to stress also that this is for a single point in moduli space. So if you want to run this for a lot of points in moduli space, these things become very much hopeless. If you want to study this for the many Calabi-Yau metrics, many Calabi-Yau manifolds, different geometries, I mean, this becomes you're hitting this wall. Also conceptually, this is very much tied to Kähler solutions. How about things when you have non-Kähler solutions? Yeah, this would have to revisit this very much. And now this is what we can do with machine learning. So yeah, very briefly. So we ask the question: okay, can machine learning help? I mean, this seems very prone to do this. Let's have a look. Again, same exercise. Write down the optimization problem that you want to solve. In this context, you can do this, for instance, looking at the Ricci tensor, yeah, and look at whether this is vanishing. This is one way of doing this. The other way of doing this is by evaluating this Monge-Ampere equation, which balances these two metrics. And the advantage of this is that this involves less derivatives. Yeah, so computationally, that's a little bit cheaper. We can do both, but this is more efficient. So whenever this is also an important lesson, I think it's always good to think about this optimization problem carefully. How can you solve it in the cheapest way? Yeah, are there more expensive ways of doing it? And can you cut the computational cost? Good. You can formulate this as such a loss function. Now this becomes a little bit more abstract. I will say a bit more about this because what you have to be careful about here is you have to evaluate this condition in the appropriate way, namely that you are integrating over this entire manifold and that you are weighing not special points, not points very with the appropriate weight. Yeah, so that you're evaluating this integral appropriately, but this can all be done. Now, if you're looking at things like celerity, again, you can formulate it in terms of what conditions have to be satisfied for the metric. And again, this is something you can put into the computer. Now, if you're going to very sophisticated Ansätze, there are also things where you have to worry about whether they are well defined across coordinate patches, and then you get conditions on the transition function. So another loss term, which basically compares metrics on different patches. Good. Again, you can do this measure. You can evaluate these integrals, and you can. This is basically by looking at the appropriate weights of playing all these games between embedding space, etc. Of seeing how you can do that with the appropriate pullback of the Fubini study metric. Good. And in the end of the day, you end up with an accuracy measure for your story, and you can ask, okay, yeah, how good are we doing for this story? So this is now, for instance, showing you again this different. So this is the accuracy that you see here on this plot, and you can ask about what happens, for instance, if you just were to choose this matrix H, which we have in the Kähler potential as the identity, and you would see such accuracies. Yeah. So you see, okay, yeah, that's where you're doing if you're doing nothing essentially, and you see, I mean, obviously interesting behaviors, but this is something obviously always to compare with, that you're not that you're doing something non-trivial. Good. Now, but in any case, we have again in a very well-defined territory. We have to just search for a function with these particular properties, and And then we can optimize it. We have to, look at derivatives of the network. Again, automatic differentiation is key. And yeah, we can do this. Now, there are multiple things you can look for. So, for instance, you can look for just making this particular ansatz, where you're just learning this capital H matrix, and from that you get the Kähler potential and the metric. You can also do a more flexible ansatz, and you get the metric out. So with taking Damian out, who would think this one would lead more accurate results than this one? Okay. Any reasons for why you think this one leads to more accurate results than this one? Yeah. This is really, again, this is the story about biasing you towards really nice solution. Basically making good guesses, yeah, for the solution, trying to limit the optimization. This is the version of variance versus bias trade-off, this whole story, to kind of look in the right direction. And this is why this is giving us much more accurate results than learning this directly. Good. Now you can again solve this in various ways. You could run this in a supervised way by running this other old algorithm by Donaldson. And set it up as a supervised problem. But again, what we can also use is to use this in an unsupervised way, in this variational way of doing things to train H directly. And again, these are not very sophisticated neural networks. They are just okay. There's a bit of hyperparameter tuning, but in the end of the day, they're not something super efficient. And then you can run the algorithm, and you can see how things go. And so, for instance, here we trained this for a moduli range between 10 and 100. And I'm showing you a couple of networks here. And I'm comparing this. So this is, again, the same resolution that you would get with Donaldson's algorithm that you would run. And this is what the accuracy that you're getting with our neural networks. And you can study also how well does this extrapolate outside of the training domain. Good. Now, yeah, in the last couple of minutes, so let me tell you a little bit more about how the implementation of these things goes and what we're doing. So these networks is basically you have to play a couple of games of what you put into this network. So it does, we have this complex parameter psi here, right? We do note that doing some feature engineering does sometimes help. So taking powers, for instance, of this whole story does help. But that's also cheap, right? I mean, we can generate this very, very quickly, and we can let the neural network decide on what to put in. It's sometimes good to have the real and the imaginary part, and sometimes to put this in absolute value and angle in. You'll have, your dense layers. And one thing, again, because these are very sparse matrices, one thing which we do find very useful is to suppress certain outputs. And we do this by having such a sigmoid as a learnable sigmoid of this beta. So this effectively can turn off certain components. Good. And basically, this is the final layer gives you the real H parameter stuff. Now, in terms of perspective, so that's the networks there. Now, and how do we stand in comparison to these other things? So one network that we were also able to run these metric networks directly. They are nevertheless, they are not as accurate. But what they are interesting for is if you are interested in something like non-Kähler solution. Yeah, so then these allow you to look there. None of these at the moment are at the analytic frontier, right? They're just numerical approximations. So one obvious question is, okay, how much does symbolic regression help us? How far can we push into the analytic regime at some point as well? And so one thing that we wanted to push was to see, okay, how can we go beyond the quintic, and to put out a framework for this. And this is where we have this ongoing project of CYJAX, where we basically provide a package which can be easily extended, but has very nice features to look for different geometries and in principle also different metrics, etc. So now what can this be used for? This can be used, for instance, to look at again, so this is again on the dwarf quintic. You can see, okay, the effect of different resolutions of your ansatz, or how accurate your ansatz is. These are things now you can also do in the package effectively. You can go to more sophisticated defining equations. So here's some situations with 2 parameters. Again, this is a lot of very straightforward work that we need to do to get there, to get to better results and to expand it. So if you see, for instance, the values here on the accuracy, they are not as good as on the previous slides. But again, these are things where you can study nicely about features of what is happening, actually, where are these accuracies, where do we lose things across moduli space, and how is the behavior in various regions. And so yeah, let me conclude. So yeah, I wanted to talk about how can we learn about mathematical structures. And I think the key message I want to give across is that we can often formulate an appropriate optimization problem to this story, and we can often solve it given appropriate coding. So but the key thing about this whole story is that we do not need to know this mathematical structure a priori, right? So we can do this without having known the metric. We can do this without knowing a Lux pair. We can search for this. What was key is that we put in a little bit about physics bias, and so to design our neural networks accordingly, that they give nice results. And what was really interesting, I think, is that we see that actually by searching for these symmetries, we also see a better performance in apples to apples comparison than to say a standard benchmark with where you're just trying to predict P dot and Q dot directly. And this is really I think mathematics in at work, effectively showing us really that using these structures is much more effective. Now, if an optimization problem is not available, this is not the end of the story. We can try things in the sense that we can try to understand the latent representations. And in some cases, we can be lucky. So for instance, we could find the symmetries of a system. Again, in the implementation side, automatic differentiation is key. And numerically harder problems such as the Calabi-Yau matrix or so, much more complicated than a gravitational two-body problem, is we can set this up as well. And so there's obviously a lot of other things about string theory flux solutions that we have been developing as well to do. And finally, as I was asked also about implementation before, this is possible, but we actually do need, it does require you some time to code up this loss function. It requires you some time to make sure the things actually converge to things. It's not something, once I've coded this up in one line, okay, it's giving me the results. So in the sense that there's a lot of tweaking that is going on under the hood. Yeah, with that, I'd like to, thank you for your attention and inform you that, in case you have people that students that are interested in going in this path, we have now started a new degree specialization where you can study physics with a specialization in AI at Munich. So please spread the word. Okay, so yeah, thank you.